All right. Hello, everyone. I think we're live. Thanks for joining us. We're really excited to have you all today to talk about a topic that we're passionate about and to co-host this with our friends over at Pinecone. So we'll get started. Just kick it off by introducing ourselves. So I'm Dan Whalen. As you can tell, my lack of beard here compared to my co-host. I come from the security side of the house, not the data science side of the house. But I'm a principal detection response engineer here at Expel. Matt, you want to introduce yourself?
Yeah, hi everybody. My name is Matt Berninger, and I'm a manager of the detection response engineering team here at Expel. And so I have some experience in doing data science research specific to cybersecurity, and before that, doing incident response and detection response activities in the cyber domain.
And if you all aren't familiar with Expel, just a quick intro to our business. So we are a cybersecurity business. Specifically, we do manage detection and response. So we help organizations identify and respond to cyber attacks. And we're co-hosting today with Pinecone. So James, you want to introduce yourself?
Yep, thank you. So I'm James. I'm the developer advocate over at Pinecone. And for those of you that are not familiar with Pinecone, we are a fully managed vector database, which basically means we make it very easy to add high performance search to applications, which might not make sense at the moment, but hopefully by the end of this presentation, it will. So.
All right, thanks, James. Let's get into it. So I wanted to give you all a sense for what you're in for today. So today we're going to talk through how we've applied some data science techniques to help with some of our security use cases at Expel. And although we're going to talk about our specific problems, our specific use cases, we wanted to cover the topic in a way that was generally applicable. So we'll start by touching on the background of our specific use case and problems, our challenges that we wanted to address. And then we're going to kick it over to James from Pinecone to lend his expertise to talk about some of the key data science concepts in play here that we ended up applying to help with our problems. And finally, we'll talk about specifically what we implemented on the Expel side of the house and the features that we're aiming to deliver as a result of those capabilities. And just as a note, before we get into the content here, we love to encourage participation in these sessions. Alyssa on the line here is going to act as our moderator. So please feel free to use the Zoom chat or use the Zoom Q&A feature to ask questions as we go throughout. And at each section break, we'll do our best to pause and see if there are any questions before we proceed. All right, so we've probably all heard the term deja vu, right? I've probably seen The Matrix more times than I can count. So like just watching that movie is a bit of a deja vu for me. There's a few definitions out there. I particularly like the second one here, something overly or unpleasantly familiar. And today we're going to talk about some examples of how deja vu was a challenge for us at Expel and how we intend to address those challenges with some data science. So I mentioned that, Expel is a cybersecurity business, right? And I want to talk a little bit about what we do on a daily basis to set the stage for the problems that we wanted to address. So as a security service, we consume what could be called an overwhelming amount of data from security technologies, from organizations, and our platform funnels that down the most important security alerts and puts those in front of our security analysts in our security operations center. So our SOC finds the order in all this chaos, and they have to decide whether to notify our customers about activity that they need to respond to. And we do this to the tune of about 1,000 alerts a day. So you can imagine, as a security analyst sitting in our security operations center on a daily basis, deja vu is a pretty common occurrence. If you're familiar with like the security space, you know that security alerts are pretty notorious for being really high volume, really repetitive, and unfortunately false positive prone. So this can be a pretty frustrating experience as an analyst, to see an alert, to swear that you've seen something similar before, but be unable to recall, that previous circumstance, that previous situation. What ends up happening is you end up having to rework that alert like it's brand new, but you have this sort of uncanny feeling that you've seen this before, and that's pretty frustrating. And unfortunately, over time, if you subject your security analyst to these sort of similar alerts and these false positives over and over and over, this can have some pretty negative effects. You may have heard about this term, alert fatigue. It's pretty common in cybersecurity, but it's not unique to cybersecurity. It's also sometimes called alarm fatigue. I like the definition here from Atlassian. An overwhelming number of alerts, you end up getting desensitized, and this can have some pretty unfortunate consequences. It can lead to missed or ignored alerts or even delayed alerts, right? And this is a very real problem for us at Expel. We definitely care about the quality of our service and even about the happiness of our analysts. So we don't want to subject them to these repetitive alerts. And we don't want to experience any of these negative consequences like increased defect rates, increased response times, and in particular, employee satisfaction or burnout. We definitely want to avoid those kinds of issues. So that's a little bit of background there about sort of the problems from the Expel side of the house. My pleasure to turn it over to James from Pinecone here to talk about some of the key concepts on the data science side that we wanted to apply here.
Thanks, Dan. So a lot of what you've said with similarity and matching similar alerts is a very similar problem in other industries. So if you think about when you search something on Google, what you're doing is kind of writing a question, some text, and Google is basically matching that to the most similar other documents or web pages that it has indexed. And it returns those back to you based on which ones are the most similar. So it's very similar to your alert fatigue, where you are clustering similar alerts, but in this case, you're actually wanting to find results that are most similar to whatever question you have. And this is also the case in Amazon or Netflix, but obviously you are probably not necessarily searching for something, at least not on purpose, but they are recommending products that are similar to products that either you or people that are similar to you are interested in. So that's a few examples of where this sort of similarity search is applied in other places. So what we'll go through in this small section is kind of how that similarity search works and what the key components are. So you can see on this on the previous page, you can see we had the feature extraction, tokenization, vectorization, distance metrics, and approximation. Now we'll just work through each one of these. So we'll start with feature extraction. Now, when you, as a person, you read a document, you don't necessarily pay attention to every single detail in that document. There's certain parts of that document that are more important than others, based on whatever it is you're searching for. So you might go straight to the document title. You think, okay, that's relevant to me. Do I know the author? Is it recent date? And then in the body of that document, you're going to kind of hone in on specific parts of or specific bits of information. And it's very similar with machine learning models and similarity search. You need to extract the relevant information because generally, depending on your use case, of course, you don't want to extract everything because then it gets quite messy. And you might also want to clean up part of the data that you're extracting. So on the right on this slide, you can see we have the sort of fake alerts. We have a timestamp, we have a little bit of text in the middle, and then we also have a directory. And you can see in the second little code box, what we've done is we've removed those timestamps because we've decided for our use case it's not particularly relevant. And we've also normalized the user directory. So where you could see users / James or Dan before, it's now just user. So that's feature extraction. And the next step after you've extracted your relevant information is to tokenize it, which is turning a series of characters like a sentence into a list of what we call tokens. And you can think of in its simplest form of tokens as simply words. And that is one step towards vectorizing our text. Now, when we say vectorize text, it's how we can convert text into a format that a computer can actually understand, because obviously a computer isn't going to understand text in the same way that we do, because text and language is very abstract and a very sort of human-centric sort of concept and thing that we as humans use. And a computer obviously isn't going to understand the meaning and concepts behind the sentence. So what we do is convert the text into a vector. And with modern machine learning methods, we can actually make sure that vector is encoded in a way that we can think of as being numerically representative of the meaning behind that text. So it's almost like the way that we understand language and words, the computer actually represents or encodes that meaning into a vector. Now, if we do that for many documents, we will probably want to go ahead, after we have done that for many documents, we want to go ahead and compare one document to other documents very quickly. And using these vectors, we can, if we move on to the next slide. Oh, so this is the vector, just a quick example. So in the top box here is just a small snippet of Python. All we're doing here is that we're importing an ML model, which is just encoding the text. So the text that we saw before, where we had those alerts that we normalized, we're just encoding those, and what you can see there is actually a vector. So that's what it looks like. Obviously, we can't read that, but that is perfect for a computer. So in this case, we're using a machine learning model. There are other methods as well. There is minhash, which is another algorithm that allows you to quickly generate these vectors. And it's very useful for both the neural method and the minhash method are useful for calculating the similarity or approximate similarity between those documents in a meaningful way. So when we say similarity, we mean semantic similarity, which we can see as the sort of the similarity in the meaning of that language. So on here, after we have those vectors, we want to compare them, as I said before, and there are a few different ways that we can compare vectors. So the first one here, Jaccard similarity, is typically what we would do when we have the tokens rather than the vectors. So what we're basically saying for Jaccard similarity is how many tokens are shared between documents or strings of text. The more that are shared, the more similar the documents are. Now, this is okay and it works, but in this case, we're only really capturing similar words, not really the meaning. So it's not perfect because tokens can be similar without being equal, and they can even be equal without actually being similar in a sort of human understanding or human comprehension way. So for example, we have the word or token bank. That could mean one of several things, such as the banking maneuver of a plane. It could also mean grassy bank. And it could also mean in the context of the Bank of England. So there's 3 different meanings there, and we have the same context. So Jacquard similarity would not understand those 3 words or tokens as being different. It would see them as being the same and return a higher similarity score, which we don't necessarily want. And the same is true for tokens that are actually different, or they are so different words like hi, hey, and hello. They all mean the same thing, but Jacquard similarity will not identify them as being similar. They will identify them as being different. So that's the drawback or the issue with Jacquard similarity. And sometimes it's not an issue, it depends on the use case. But if we want to capture the meaning of text, it doesn't really work for us. So what we can do is we use the vectors that we created before. So those vectors, we can't really compare using Jacquard similarity, and instead we use something like Euclidean distance or cosine similarity. Now, on the right, you can kind of see the top 2 points. They have a line going in between them, and that is the Euclidean distance. It's simply the distance between those 2 vectors. A cosine similarity is slightly different. So you are going from the origin point, and you are looking at the angle between 2 vectors, and you don't really care about how far away those vectors are from each other in terms of distance. You're just looking at the actual angle between them. So basically, there are a lot of different ways to deal with this and calculate similarity that work either better or worse in different use cases. So when we have a database and we have all of these vectors or these dense vectors, which are the vectors of floats that we described before, you would typically in these databases have many vectors for most use cases. So a database containing 1 million of these vectors, it's just 1 million documents or 1 million sentences, and in a lot of modern applications, that's not actually a big data set size. You get much larger. So if you think about, okay, we need to calculate the distance or similarity between, say, one new query vector. So imagine you're asking a question to Google, you have your one new sentence, which is converted into a vector, and you want to compare that to all of the other vectors that are already in your database. Let's say you only have 1 million of those. You need to perform 1 million comparisons. And that is not going to be that fast. And when you're doing this comparison between all of the vectors in your database, we would refer to this as k nearest neighbors. Now, this sort of exhaustive search where you're comparing everything is too slow, even for 1 million vectors, and for more, it's even slower. And for most use cases, you need something that's fast. So this is where you would use a tool like Pinecone. So Pinecone uses something called an approximate nearest neighbor search, and that basically works by, well, it covers a variety of algorithms, that simply allow us to approximate the search. So we're not actually searching through the whole index, but we're actually identifying which vectors are kind of within the range or similar range to our query vector. And we then restrict our search to only those vectors and compare between our query vector and that restricted range, which obviously means we can perform the search much faster. Now, with approximate neighbors, we can reduce search times that would have previously taken tens of seconds or more with k-nearest neighbors to tens of milliseconds or even less. So it is a very efficient way of searching. And there is a slight cost in terms of accuracy, but it's very minor. In most cases, it's definitely worth the improvement in search times. So I think the next slide, so we have a quick example of how we would do this in Python, and a little bit of Pinecone at the bottom there as well. So what we have is our query at the top. So we have this sum change alert in any location. And if you remember the fake alerts that we had before, we had things like file change alert in directory change alert in another directory, and also new login location, which you can see them at the bottom. And what we're doing here is comparing the meaning in each of those sentences or alerts to our query sentence, which is some change alert in any location, and we're returning the ones that are most similar. And what you can see at the bottom there is the similarity score. So you can see the first 4, which are either file change or directory change, score much higher than the final one, which is a new login location. So we're searching in a more human-centric way and actually defining the meaning behind that and returning, and not based on matching words, but based on the meaning behind our query. So I think that's it for our section. If you do have any questions about that, please just drop them in the Q&A section.
Thank you, James. That was awesome. Alyssa, do we have any questions? I don't see any.
Yeah, Dan.
All right. Yeah, so James did a great job there of sort of providing an overview of the key data science concepts, and those are generally applicable, right? We're talking about security here, but like regardless of your use case, you can apply those concepts to your problem in a very similar way. And so what we wanted to do in this next section was talk specifically, again, going back to our problem of alert fatigue. How do we take these key concepts, apply them in our domain, which is security, and what are some of the like domain unique challenges and problems that we had to solve in doing so? And I really liked what James said when he was talking about really the first phase of this, which is defining your document and extracting the relevant features, right? This absolutely has security specific challenges, right? If we think about a security alert as a document, one of the things James mentioned again is you don't want to extract everything as a feature. That is absolutely true for security alerts, right? We have a mix of very useful information or features, as well as a bunch of information that would potentially pollute our searches and make things just a little bit crazy. So a good example of information that we would want to include as a feature, evidence like IP address, host names, usernames, file names, things that are very relevant and make that security alert, special and unique. But there's also a lot of data in security alerts in general that maybe might not be useful to extract as a feature. Things like a unique identifier or a GUID, or as James mentioned, a timestamp. Those are things that we want to exclude or potentially modify before including as a feature. Otherwise, we end up with vectors that are overly specific, and we end up getting really weird results. So one of the sort of key challenges in applying sort of these concepts to security was, what features do we care about for a security alert, and what's the right way to extract them? Now, there's also some, there's this concept of enrichment in security, and I think this applies generally as well, but there may be information that's related to a security alert that doesn't actually exist in the document as it is. A good example is, we might have a security alert with an IP address, a public IP address. And, the security alert may not contain information like, hey, well, what organization owns that public IP address? What ASN does that IP address belong to? What country does it belong to? And that's information that we can actually gather from external sources and pull in as an additional feature. And we really, we refer to that process as enrichment. And we've had great success with this as a process in general. And we've got a bunch of services here that we use pretty heavily at Expel and would recommend for this purpose. So for example, if you have IP addresses, there's a service out there, ipinfo.io, that we love. And they give you all kinds of great information about an IP address that you can use to, again, enrich that document. Whether that's getting the geolocation information, whether it's, a VPN server, a proxy server, a Tor server, what organization owns it. That's all really useful information that we can pull in and include as part of our document vectors. Similarly, if you have a file, like a file hash, VirusTotal is a very useful service for enriching that information as well. And actually, recently we've been exploring how to use marketing information like from Clearbit and ZoomInfo and those sorts of organizations to enrich email addresses and domains. So you can imagine if you had an email address, like dan.whalen@expel.io, well, who is he? What's his role in the organization? That sort of information is very valuable as we think about finding similar alerts as well.
All right, who is Dan Whalen indeed? Thanks, Dan, for teeing this up. So as Dan was talking, we have artifacts that come through alerts that have information that if we included in the document and therefore in the vector representation could lead to, sometimes referred to as spurious correlations in the model, right? So we've gone over a couple different normalization examples, but here's another one here. So we do a lot of this where we look at these different artifacts, whether it's a file path, whether it's even, you saw the user agent in a previous slide. So we have these sort of complex, rich data fields. And these data fields contain a lot of really useful information, but they also contain information that needs to be normalized out. And from a data science perspective, if we were to include, for example, the username in a path like this, or even the file number in the file name, this can lead to what's called overfitting as well, where you're actually now training your model or your representation of your documents to be overly specific to, let's say, Dan Whalen. And what we don't want to do is find things that are similar to, say, this artifact because it also has Dan Whalen. We want to find behavioral similarity or more generalizable similarity. So that is definitely a big step in our process as we prepare the data for the tokenization step, which I will go into next. All right, so I know that every domain is tricky in its own way. I'm biased towards security. If you've done NLP, with sort of natural language, with English, tokenization is a relatively straightforward step. James had mentioned some of these steps earlier. And so you have issues where you want to do stuff like what's called lemmatization, where you may have words that are just sort of different derivations of the same word, say conjugations of the same verb. You may have stop words, a, the, is, etc. And there are a lot of toolkits that are out there to help you sort of tokenize natural language. NLTK is one, Spacey is another one if you've done this sort of work. When you're dealing with cybersecurity artifacts, you're not dealing with natural language, and that poses an issue when you're doing tokenization. So, not just the file path we saw on the previous slide or the user agent, the one before that, but here is a bash script, for example. Where's the tokens here? Well, As someone who's written a lot of regex to try and solve this problem, I can tell you it gets very complicated very quickly. And it actually, there's nesting and there's loops. And so cybersecurity artifacts contain a ton of information in a very small amount of space, or a small amount of characters sometimes. And so a challenge for us is building out the tokenization stuff so that we're properly representing those distinct bits of information so that we can pass them to the vectorization step in sort of an intelligent way. If we were to split on white space, for example, in this document, we might be missing a lot of interesting things like equal signs or quotations, or the carets that are piping output into another process, right? The semicolons that are indicating the end of a command. So those are all things that have real semantic meaning that we want to make sure we're representing. And we have found that this step in cybersecurity is probably, in my experience, the highest return on investment of just sort of like labor in figuring out the better way to tokenize these sorts of documents. So next slide, we'll talk about vectorization. So James gave a really good overview of different vectorization methods. And so just to sort of come back to that in the cybersecurity context, the vectorization also matters. As James had alluded to, you may have tokens that are exactly the same, right? And if you're just doing, you're just counting those tokens and not necessarily the context in which they're presented, you might be calling them the exact same thing when in fact they're the same word or the same token used in different contexts, or vice versa. You could have different tokens meaning the same thing. So vectorization really does matter. And again, as alluded to earlier, the challenge we have is how much semantic meaning we want to bring in, how specific we want to get with that representation, and then also the downstream speed of what that pairwise similarity calculation is going to be. So James mentioned min hash. Min hash is very fast, and it basically, very hand wavy, but it creates a hash of those tokens, and it allows you to do things like Jacquard similarity, for example, to see what the overlap between two documents is. It's fast. It can be done document by document and doesn't require knowledge of the entire corpus, so you can do it relatively quickly. Whereas TF, IDF, or term frequency inverse document frequency is a sort of canonical traditional way of encoding meaning in natural language processing. And that requires the entire corpus to calculate the document frequencies of certain tokens across the entire corpus. So to the example James gave, when you have one new document and 1 million pre-existing documents, if you were doing TF-IDF, you would have to recalculate the vectors for all of those documents now because your population has now shifted. So the calculations become really problematic speed-wise when you're doing something like a TF-IDF representation and you're doing pairwise similarity calculations for very large sparse vectors. But at the same time, if you are optimizing for speed, you might be underfitting or over generalizing some of your similarities. So we're invested in sort of exploring this space and trying to optimize that. The cybersecurity domain also presents a couple interesting avenues for things like term frequency. Term frequency is used to indicate the importance of a term within say a book or a magazine or a document. For cybersecurity, our alerts don't tend to have very high term frequencies unless you're dealing with a massive script per se or some really large bit of text. But for something like a logon, that IP might appear once, in the artifact. So your term frequency is going to be 1. So we're looking at ways to sort of learn different weightings we may know that, for example, the IP address is more important than, say, the username or something in a particular family of alerts. So we want to encode that meaning as well. So we're exploring this space. There's a lot of work to be done here, but I wanted to call that out, that it is this interplay between speed, which is important, and accuracy or sort of full semantic representation, which is also important. Oh, and a link to, there's a Pinecone blog that goes over a bunch of these different approaches that I really like. So definitely check that out. Next slide. All right, back to Dan.
So we've talked a lot about sort of conceptually how to solve some of these problems and some of the concepts that you can apply from data science. But we also wanted to talk about, like, how do you go from research to actually delivering a feature in production? That's something that we're passionate about. And, as we thought about this problem and looked around into the future, we sort of pretty quickly realized that Similarity as a platform feature could solve a lot of problems for us over the coming years, not just for this one specific use case, but there's many ways that we can apply that in our business over time. And so, as we thought about that, we wanted Similarity to essentially be a feature of our platform that any engineering team in our organization could rely on and leverage to power new features, over time. And so how do we go about building that? We sort of, rough sketched out, a napkin drawing that looks something like this, right? We have a bunch of documents of different types across our organization. A good example of that document is, again, that security alert, but there's other types of documents, in our platform as well that we may want to accommodate over time. We want to be able to vectorize those documents. We want our developers to be able to control how that process happens. So how do you take the document that you have all this intuition about, how do you turn that into vectors? That's something that you as a developer really have to own and understand the nuance there. But then as a platform feature, we wanted to be able to store these vectors, and we wanted to provide a fast similarity search across those vectors that you've stored. And again, once we have this, we know, okay, well, we can start to deliver all kinds of really cool features like, make recommendations based on similar alerts we've seen in the past. We can power alert quality control. We can do all sorts of cool things with grouping. There's all sorts of really cool stuff that we knew this would unlock if we could build this architecture. And one of the things that was important to us as we thought about this kind of architecture, like there's pieces of this that we knew we had to own as Expel. And that's really this first two steps here. Like we own the documents, and we need to own turning those documents into vectors. There's a lot of domain specific stuff. There's a lot of use case specific stuff there. And so we really need to own that part of the process. We can't really farm that out easily to someone else. But, we also don't want to go reinvent the wheel or build something when there's a solution out there that works really well. So, as part of, planning for this architecture, we looked around at a bunch of different vectors or a bunch of different services to see what was out there. Like, how can we store vectors? How can we provide, similarity search? Is that something we can just buy and pay for instead of trying to, reinvent internally? And that's, how we stumbled upon Pinecone, of course. In doing that, again, we sort of found that, yes, you can pay for vector search as a service. You can't really pay for this vectorization piece unless you have really generic documents that, are pretty, pretty common. So there's a couple of things that we built to make this architecture happen. I saw a question about, what kind of libraries are out there to turn documents into vectors, into vector embeddings. And we knew that, again, we were going to have many use cases over time, new types of documents, new ways to vectorize them. And we wanted to centralize all that into one place. Like, we didn't want every developer to have to go implement from scratch a new way to vectorize their specific document. We wanted to provide them a framework in which they could operate that gave them all the helpful tools to, tools along the way to make that process easy and ultimately make experimenting and productionizing that research as frictionless as possible. So one of the things we did is we built a common library that we call Arnie. It's a Python library. We love to name things at Expel. That's just what we do. Arnie stands for Artifact Normalization and Intelligent Encoding, and it's intended to be a security domain-specific security library that can take security documents, security artifacts, and turn those into vector embeddings really quickly and easily. Without needing to know much about the underlying data science. You just need to know how to rip apart and extract the right features from that document and encode that into the framework. And again, the second piece of this puzzle was how to provide vector search. We looked at a bunch of different vendors, and I swear Pinecone is not paying me to say this, but they made our decision very, very easy. It was incredibly easy to experiment with. They had a free tier that we experimented with. On their free tier, we loaded up about 1 million vectors just to test performance. Our requirements were sub-second, and they were giving us on their free tier 160 millisecond search latency, which is well beyond what we were looking for. And in fact, I've heard that today is probably half that. They're continually improving. So we were really happy. It was very easy to experiment with them and very easy to onboard. So they made our decision there. They're really, really easy. And so again, we talked a little bit about the concepts, the architecture. We wanted to also touch on the last mile, like what features at the end of the day do we actually want to deliver, and how do we want to measure impact, and ultimately what are we, what kind of metrics are we driving with these features? So I'll turn it back over to Matt to talk about some of that work.
Well, before we hop into the last mile here, I know we have a couple of questions that came through, so I figured we'd take this time to answer some of those. I saw some really good questions on transformers, so hopefully I cover that. One of the questions is, are transformers fine-tuned on code programming languages, for example, T5, useful for security-specific tokens, URLs, paths, etc.? So I will say that transformers are everywhere these days, and they're doing a lot of really interesting things, and they've been wildly successful in a lot of different applications. So we'd be stupid not to explore that, and it's something that we are actively looking at. I will, for the code specific stuff, one of the challenges we have is the diversity of different code languages that we encounter in different alerts. And in addition, we encounter a lot of obfuscated code. So when you're writing actual functional code, you're not going to hopefully try to make it hard to read, but malicious actors do actively make it hard to read, right? They're trying to make it hard to read the code. So there's that challenge. Additionally, a lot of the code we're dealing with is scripting languages or pre-compiled or uncompiled code on the command line. So it doesn't neatly fit into sort of a co-pilot type transformer space. That being said, we're interested in seeing if that can work, but we're poking at it as well. It's definitely a great avenue for research. That's all I can say there. And then there were a couple other questions, and I think, James, you may have answered them in chat on the Pinecone stuff, if you want to expound on any of that.
Yeah, I can do. So find that. So the first question, or actually the second question from Stefan was, does Pinecone provide any pre-processing step for computing the embeddings, or is it assumed that the logs or text is already vectorized? So for that, Pinecone would expect whatever it is you're feeding into Pinecone to already be vectorized. So you would need to pre-process your text or logs and vectorize them, and then send them to Pinecone. And the other question from Stefan, which Greg answered, was, is ANN the only similarity metric available in Pinecone? So in Pinecone, you create a approximate nearest neighbors index, which can use one of three similarity metrics, which is cosine similarity and Euclidean distance, which we covered in the earlier slides, and also dot product similarity as well. There was also Daniel's question. So the question was, the example using sentence transformer, which I assume is similar to Word2Vec, so it's similar. Are there any other transformers that use specialized data like IP addresses to create vector embeddings? And I think Matt already kind of covered that a moment ago. So you have transformers for a lot of different use cases, and it would definitely I think there's a real possibility that could be applied, but I personally haven't seen anything. And you probably, if there isn't anything already there, you would need to train your own transformer and figure out how to do that. But I wouldn't be surprised if there either is something already or it's possible. I think that's all of the questions.
Yeah, I'll answer just the encoding one, and then we'll save the metrics one and the open source and library one for the end, if that's okay. So yeah, Dan answered in chat, but certainly obfuscation wise, we see a lot of base64 encoding, and then inside that you can see gzip, gzip compression and all sorts of wild stuff. So we're aware of those, right, as analysts, and we try to factor that into our tokenization process. That being said, as Dan mentioned, you can go crazy trying to deobfuscate some of this stuff. So we try to get sort of good enough, right? and I think that will speak to sort of the metrics, right? How far do you really need to go, and are at a certain point, if you're going 4 or 5 levels of obfuscation down, are you perhaps overfitting in that sense? So definitely something to consider, and something we encounter quite often, depending on the artifact type. All right, thank you for awesome questions. All right, so the last mile, what do we do with all this? The first slide. Yep. So, similar experience if you use a streaming service and they're saying, hey, Matt, I saw you watch Dune. You might be interested in the Foundation. Two things I'm watching right now. So recommendations, right? How do we make recommendations to analysts? So we might say, hey, you saw this alert pops up in the queue. Hey, we've actually seen 17 really similar alerts to this, and they got this label. The following decision was made about those alerts, so you might want to check those out. So that's a pretty straightforward use case for how we might use something like this. Again, we want this experience to happen we talk a lot about optimizing the analyst moment at Expel, and we want this to happen in the moment. So that's where that latency really matters, and that speed really matters to us, because we want this as soon as the analyst gets to an alert. We don't want to slow down their triage of that alert, because it may be something that's very bad and we need to act on it really fast. So that's why the speed is important. And I should mention Ruxy. If you're wondering who Ruxy is our robot, one of our robots that reaches out and does things like enrichment and hitting services like the Similarity service to make these recommendations. All right, and then we also have an alert quality control queue. So we retroactively will go through alerts that have been reviewed, and we want to sample from that population to make sure we're making right decisions, and sort of an orthogonally different or an orthogonal approach to sort of the linear queue that we run through in the SOC. And this helps us find things like maybe, if we made the wrong decision or something, or if we didn't investigate something when we should have, or did when we shouldn't have, or we could have made a better decision. So this is a way of continually improving our process. And the question becomes, well, how do we intelligently sample these things, right? Previously, we were sort of randomly sampling them, but we thought, well, is there a better way to sample alerts that might be of particular interest? And so what we look for is discrepancies between an alert and sort of an alert that has been dispositioned, or a label has been applied, and then the alerts in its immediate similarity neighborhood and the labels that were applied to them. So we may, in this alert quality control queue, say something like, hey, this alert was closed as benign, for example, but a lot of the other alerts around it look malicious. So we might want to take another look at that one. And so that helps us sort of understand potential improvements to our alert quality control. And then there's a lot of other applications, right? Again, as Dan was mentioning earlier, if given that we can tokenize and vectorize meaningfully and make that conversion from the highly complex semantic space into the vector space, that unlocks a lot of different possibilities. So we can look at things like brand impersonation. That's a sort of a social media security thing that's come up in recent years. Spear phishing websites, oftentimes attackers will send websites or links to websites that look just like the login page. Email classification, that's a pretty well-tread space in the security space. I'd say particularly of importance is behavioral detection. Behavioral detections are becoming more and more important as more and more companies are moving to cloud applications and things like that. We were talking a lot about base64 obfuscation and endpoint artifacts. Those are very rich security artifacts, and you can get a lot of information out of them. When you're looking at something like an anomalous logon, there's not as much forensic artifacting to do there. You're not encoding or decoding something. You're not reverse engineering something. You're just looking at someone's logon and deciding whether or not it was malicious. And so adding context to that, using something like Similarity and looking around the population of alerts and saying, well, what looks similar to this from maybe a probability perspective within that domain or that customer, that can be really helpful to giving the analyst more threads to pull to make those decisions. So that's definitely something we're looking at. And then campaign identification, again, looking across different domains and sort of surfaces. Can we see similarities between the way that malicious behavior is occurring and maybe identify a campaign? The last couple of days have been particularly interesting if you've been paying attention in cybersecurity, because there's been a lot going on of similar nature, referencing the Log4j vulnerability, of course. So there's a lot of applications we can use here, and we're excited to explore all of them. And I think that is the last one before, yep, Q&A.
Yeah, so we want to circle back to the open source thing. Matt, you want to take it or I can take it?
All you, Dan.
All right. The answer is not yet, but it will happen. Before we even created the repository in GitHub, we knew that we wanted to open source this work. Our first goal is to get our first use case in production. The library is changing a lot right now because we're learning about what we need as we're driving towards production. But once we've landed, we're going to be in a place, I think, where we can circle back and open source the components, the applicable components of Arnie there. So that is absolutely something that we want to do.
Cool, and I'll take the generalize. Are you able to generalize data enough in order to make predictions against customers in the same verticals or localities? Seeing AWS people get it with X, or on the fly, adjusting sensitivity across the rest of the data coming from the sources. So I think, if I'm correctly understanding, generalized behaviors within different environments, right? So you're talking about logon similarity. That's where the sort of the probability, like encoding probability or prevalence numbers becomes actually a vector feature, right? And if I'm understanding this question correctly, it's that you could have customer A or environment A has its own sort of logon behavior and distribution. And then you have environment B that has its own logon distribution. Can you use information from environment B to inform the maliciousness or not maliciousness of a logon in environment A? And if that's the question, yes, that's something we want, right? Because we don't want to have to train individual model sort of specifics for each specific environment. We can use information, but if we can gain information about what anomalous, logons look like in general, or anomalous API usage or what have you in the application looks like in general, we want to use that information across environments. I can't say that we're doing that super successfully, but it's definitely something we're exploring with this approach. And so what I was mentioning with probability is like using the prevalence of a particular username or IP or ASN in an environment, and instead of encoding that specific thing, encoding the prevalence of that thing as the actual token or as the value that you put into the vector, right? Where now Dan Whalen isn't Dan Whalen. Dan Whalen is just a percentage of logons in a given environment. And that can translate across customer environments. So hopefully I answered some of that question. Cool, thank you, Jeremy.
I see another question here in the Q&A. This seems to be a new way to do what SOAR technology does. How is it different? And I think this is referring to maybe Expel as a service. How is Expel different than a SOAR technology? I'll give a short answer here. Happy to chat about this in more detail. A SOAR product, essentially, if you're not familiar with that, is a security orchestration automation platform. It's a product that you buy or you pay for as a service. And essentially, you as a customer own configuring and managing that product to do to make it do what you need to for your use cases in your organization. Expel is a managed platform from end to end. So we manage essentially all of that with our platform. We've got security analysts. Our platform connects directly to your security technologies to get signal. We own all the automation at the end of the day. And we just tell you what you need to do about what's happening in your environment. So it's kind of a managed versus a managed service versus something that you own and operate yourself is the primary difference there.
Cool. And I want to make sure I answer that metrics question that was asked earlier. I realized I skipped over it. So one of the ways that we're evaluating our approach for different use cases, right, is let's take the quality control queue, for example. How often, so when we send the quality control list basically back to our quality control process, we ask two things. One, did this result in the change of that label? So did we show you something that was actually informationally useful that resulted in saying, oh, we actually, there was an improvement to be made here and we ended up changing it. So that's obviously a strong signal that we would use to say, okay, we're doing something right. And secondly, we asked the analyst, even if you didn't change it, do you understand why we gave you these other things to look at? Do you see any meaningful similarity between these things? So the analyst can say, I have no idea why you showed me these other alerts, Matt. This wasn't helpful at all in reviewing why we closed this alert, or did we find it relevant? So those two signals allow us to reevaluate the approach, because ultimately that's what we want to show. Because it's somewhat an unsupervised use case, and so we want to get some of those labels back to the analyst. To another use case, when we're doing something like maybe trying to aggregate or correlate alerts together that might be part of the same intrusion or the same campaign, we actually have historical information, right? Because we have a lot of security intrusions that we've reviewed in the past. And so we will retroactively run this model against those to see how much of that cluster it actually put together in the same neighborhood or called similar. So we can look at it and say, well, if we had just landed on this alert and didn't know about any of this other stuff that was going on at the time, would it have pivoted us to these other alerts in the investigation? And we can use that percentage of occurrence as a sort of benchmark metric to see if we're improving or not. And that's super important because, of course, we can talk all day about different approaches to tokenization and vectorization. But if we ultimately don't have a scoreboard to say, okay, we did better or worse, we're just kind of talking past each other. So that's absolutely critical to evaluating our approach here.
Awesome. I'm looking through the questions here. Did we hit everything? I think we may have.
Up a note if we didn't answer your question. But
yep,
fantastic questions.
Drop it in again. All right. Great questions, everyone. Thank you so much for participating. It's a lot of fun when people have good questions. So, well, we'll wrap up here. Again, thanks all for the participation. Thanks for joining. We had a lot of fun. We'll leave you with a couple of resources here. So you can learn more about Expel on the left here, learn more about Pinecone in the middle. And actually, James from Pinecone, you saw some of the screenshots throughout this presentation. You can view that entire notebook in Google Colab and play along with it on the right there by following that link. So I highly encourage you to do that if you want to tinker with us. And if you register, we'll also shoot you the slides as well as the recording at some point of this presentation as well. So again, thanks a lot, everyone. We had a blast.